Hey, what's up, logic fans? Welcome to our fourth video on axioms and central syntactic concepts. So we're looking at this particular string and we're trying to prove that it's a theorem of logic. So far what we've done is we've reverse engineered this string from its, sort of initial form, just like this, to a form that looks like this. And we can kind of recognize here, oh, okay, I've got this LEM embedded in here, but I've got this whole thing I'm not really sure how to get yet. Well, here's an interesting little problem-solving technique. We know that since we're doing a proof, we're not going to have any premises, so we're going to have to start with an axiom. Now, it's a pretty good bet at this point that our axiom is going to be LEM and that it's going to be A or not A. Okay? So that's just because I'm sort of looking off of what goes here. And now the question is can I get from this thing to this whole line somehow? How can I get from this to this? And once you see this little trick, you'll know how to solve these types of problems in the future. So pause now and see if you can get from this guy in your syntactic proof to this guy. Pause now. Okay, so for those of you who have been able to figure it out, great, but this was just by the rule add. So we had it not be. And now look, we've got this thing here, and now we're just going to manipulate it all the way back up to this desired form. So what we do is now we got to go, from this guy all the way up. So we'll just take our next line. He's going to go right here. Okay, and the line after that is going to be this guy. And the line after this is going to be this line. Oops, didn't quite catch it. It's going to be this line. And after that, it's going to be this line. And then, of course, the final line is going to be our finished product, and we've got to fill in our rationale. So how did we get from this line to this line, right? Well, this looks just like it was COM. Right, so that's COM on one end. You can use, these to help you out. All right, it's just the reverse process. So this looks like it was a SOS. Oh, sorry, this was COM on 2. This was a SOS on 3. Right, and this is going to be COM on 4, and this is going to be IMPLA on 5. Right, and this is going to be IMPLA on 6. Okay, and that's QED. All right, I mean, this is the syntactic proof. Now, it's kind of interesting, right? If you don't do the reverse engineering project, right? So some people, if you grow up in the logic school of hard knocks, all right? So in the logic school of hard knocks, what happens is your professor puts this in front of you and says, prove that that's a theorem. And you look at it and you go, I have no idea how to do that because I don't have any premises. I don't even have something to start with to start manipulating. Right? And then the professor puts this in front of you. Here's the proof. And then you can kind of go through this and you can say, okay, I see that all this works, but how on earth did you have any clue how to, that was what you were supposed to do? Our answer is we've got a reverse engineering process. Okay? So we reverse engineered the thing. And that's what gave us the clue for how to produce this nice, neat, beautiful proof that this string of symbols is in fact a theorem of logic. Now, I want to emphasize, you could have done this using LNC, so I'm going to show you how that works really quickly. So some of you might have tried to solve it this way, and it's a perfectly fine way to do it, all right? But you might have noticed, okay, I'm going to try to get my A's together immediately. And if you try to get the A's together immediately, the first thing you would do on your reverse engineering scheme is you would get not A implies not B, and that's by trans on 1, okay? And then to bring the two A's together, of course, what you would get is you would get A and not A implies not B. And if you remember what rule that is, good for you, okay? But that's going to be exportation on 2. So if you saw this, this is great. And now look at how close to a contradiction you are. Okay? And in fact, you can almost see the not here if you just change this to an or. Right? So that's what we're going to do here. We're going to go Control C, boom, we're going to change this to a not, we're going to change this to an or, and what rule is that? Well, that is impla on 3. And voila, check this out. I've got an application of LNC right there. So without further ado, I'm going to say, okay, this is definitely a good time to use LNC in this form. So I'm going to write it like this, and that's going to be my LNC. And then I need to get from that to this thing somehow. Well, we're going to use our little add trick to do that. So we'll go like this, or not be by add. Okay, and then it's just a matter of, now that I've got this thing here, just going back up, right? So all I'm going to do one by one is put these suckers in here. 3, 2, so this should be 4 now. It's line 4 and line 1, which we're going to call line 5, and our particular deduction over here. And of course these are no longer needed. Delete entire row. And we got to fill in our rationale. So how did I get from this guy to this guy? Well, that looks like it was impla on 2, and then it looks like this was exportation on 3, and then this of course was trans. So I'm just going backwards here. Right, this is trans on 4. And here's a proof that this string of symbols is in fact a theorem of logic. Okay, so that's all pretty nifty stuff, all right, to think about. And you can go either way here, all right. You can just sort of, you can either go with LEM or you can go with LNC. In this case, the LNC solution was a bit more compact. Instead of 7 lines, we've got 5. But again, the efficiency question, what's the most efficient way? That's a really neat and intriguing question. It's a really fantastic CS type of question. But for beginning logic, we're not worried if you do the proof in the most efficient way or not. Ask your professor if you're in a different class other than mine. What their demands are in that respect. But for us, I don't care if you take 100 lines to do it. I mean, I might not be happy because I got to read it, but as long as it's an actual proof of it, that's perfectly fair. Okay. All right. Let's investigate some more of these concepts and look at more examples of reverse engineering and how to use our axioms to prove theorems of logic. Right? You do not need to investigate the world to discover that this proposition is true. Okay, you can syntactically deduce it from logic alone. Pretty nifty. Now let's stick with this example so I can make the following point, and it's important. So we proved that this was a theorem. Notice that we can take this and we can think about it in terms of a, you could think about it in terms of a, in terms of propositional variables, right? You could think about its sort of characteristic form instead of the capital letters here, the propositions. And notice that, if we sort of help ourselves to all of the same rules, we could prove that this is a theorem too. This is sort of like a theorem form or something like that. So for example, it would look like this. So here we have our proof that we just did that this is a theorem, and here we have a similar proof in terms of P's and Q's that this is a theorem. So it's kind of an interesting thing, okay? But one thing to think about is that this guy here is actually telling us a heck of a lot more than this guy here is. This guy here is a particular proposition for particular statements A and B. This here is representing the general form. It's the characteristic form of this. And yet we can prove using a very similar procedure, right? This is the exact same procedure that this form is a theorem. And so intuitively you can sort of see that, okay, any substitution instance of this form is also going to be a theorem of logic. And it's going to be a theorem of logic provable in the same way that the general form here is provable. Right? And so what's kind of cool about this is that we're now stating this sort of theorem in terms of propositional variables, but it's giving us much more general information. It's saying, look, anything of this form is provable, right? And so if we look at this, we can sort of see like, okay, this is sort of saying like, look, if the consequent of a conditional is true, so if this is true, then anything implies it. So it's telling us sort of something fundamental in logic about the general nature of conditionals, right? That's the point. And so sometimes textbooks and professors present, right, their theorems in terms of the lowercase variables because they're trying to get you to think about the more general features of logic. Again, this is showing you that any substitution instance of this is in fact a theorem provable in this sort of general way, okay? And so that's a really, really nifty thing. And on that note, let me show you some examples of some famous sort of form theorems, okay? So here's a table you can find in the textbook of some famous sort of, form theorems, okay? So these all have historical significance and they tell us something very interesting in general about the nature of logic and what can be proven and what cannot, okay? So here's one we just did, stated slightly differently, but same idea. Let's take a look at conjunction elimination, for example, okay? This basically says if a conjunction is true, then the left conjunct is true, right? And this is provable as a general feature of logic, right? And that's to be expected. Notice also that conjunction, disjunction here, if a conjunction is true, so is the sort of corresponding disjunction. Notice this does not work the other way around. It is not a theorem that if P or Q, then P and Q, right? And you should be able to sort of get yourself to appreciate that by thinking about it semantically for a second. So this only works one direction. Yeah, and these are all famous cases. Idempotence, the miraculous consequence. These are all famous ones. One I'm going to, maybe I'll talk about two of them right here. So we're probably going to have to spill into another video to get another example in. But let me talk about explosion for a second. Explosion is a very famous theorem, and what it kind of shows you generally is that if a contradiction is true, if P is both true and false, then anything follows. And one of the homework problems has you prove this as a theorem of logic, okay? So it's a good reason to ban contradictions from our logic, right? Because if a contradiction holds, you can literally prove anything Q that you like. So Q could be unicorns exist, there is no people, whatever, any crazy thing you want to prove. If you grant a contradiction, you can then establish anything you like. So we better not allow any contradictions, right? So that's the principle of explosion. The idea is what follows from a contradiction explodes. Everything follows, okay? The other one I want to talk about and draw to your attention here, and I highly encourage you to discuss these with your instructor, is monotonic. This one looks pretty bad, but this is actually indicating something very deep and profound and very important. And so if you don't encounter this anywhere else, it's good that you encounter it here. This says, provided that a conditional is true, provided that P implies Q, then P along with R will still imply Q. So, in other words, if this thing implies this thing, then when we add any new information, you're still going to get the same implications. Okay? So logic, bivalent logic, is like this. If one thing implies something, then that thing, in addition to anything else, is still going to make the same implication. This is in stark contrast to statistical reasoning, okay, where very roughly stated, sometimes the presence of new additional need. So sometimes you're looking at like, yeah, P strongly suggests that Q is the case, but now that I've gotten this new information R, maybe I don't infer Q anymore. Okay, and so statistical reasoning is non-monotonic, but our reasoning here in deductive logic is monotonic. So this is a very interesting principle, and one of the homework problems does have you prove it. I am going to do one more brief video for this section to give you just a little bit more practice on a harder theorem proof, okay? All right, so we'll catch you on the next video, 3.5E.